Okay, so thanks for the invitation. I hope you hear me well and you see my slides entirely. Yes, I'm going to speak about complexes of oriented matrices, and as was kind of requested, I would also like to talk about them. This is several works that I will kind of touch upon in the talk, and the co-authors, the most important ones at least, are on the right. It's Hans-Jürgen Bandruck from Hamburg, Victor Chapoy from Marseille, and Zidane Matz from Ljubljana, who was my PhD student. So these are 4 topics basically in the talks that I will cover, which are complexes of oriented matrices, which is the first thing I will very slowly introduce, and I think this will be probably accessible, and I will also kind of announce why they might be important or connected to other areas. And then I will speak about tope graphs of complexes of oriented matrices, which are graphs associated to these, and they can be characterized and they behave pretty nicely. And then I will very quickly talk about 2 applications of tope graphs in this area. One is about simplicial cells in oriented matrices, and the other is about corners in complexes of oriented matrices. So I'll explain later what this means. Okay, so let's start with the realizable setting of a complex of oriented matrix. So this is kind of what we always have in mind. You take an affine hyperplane arrangement in Euclidean space, and you intersect it with an open convex set. Okay, that's kind of the geometric object that whose combinatorics you want to capture. And how you do it, for every point X in this convex set, you will code its position relative to the hyperplane arrangement. So how do we do this? First, so every hyperplane splits this convex set into 2 halves. I assign kind of arbitrary, one side positive, the other negative. And then X now in every coordinate, so it has X will get assigned a sign vector, which in every coordinate, which has a coordinate for every of the hyperplanes. And in the coordinates is minus if it is a negative on the negative side of that hyperplane, 0 it is if it is on that hyperplane, and plus if it is on the positive side of that hyperplane. Okay? That's a very basic but important idea here. So that's how, for instance, the second coordinate of this guy is 0 because lies on the second hyperplane. However, the last one, for instance, is plus because the 6th hyperplane has it on its positive side. The little arrow indicates the positive side of hyperplane. Okay, so this you can do, and this you can do actually. So if you think about it, as long as I move my point within a cell of this arrangement, this sign vector will not change. Yes, if I move this little guy inside this cell, it will always be encoding the same. It will always get assigned the same sign vector. So actually, I'm assigning the sign vectors to cells, not to points. And if I do this with all the cells that are inside this convex set, then I get a set of sign vectors, which is called the covectors. And this is the object. So this is what is called a realizable complex of oriented matrices. They're always called COM. So this consists of a ground set, which corresponds to the set of hyperplanes, and the set of covectors, which are these sign vectors of length E. COM stands for 2 things, which was funny. When we wrote this paper, we were kind of not agreeing how to call them or what to call them, but good thing is that both had the same abbreviation, so we just called them COM. I prefer the complex of oriented matrices. I will tell you why later. but the other name is conditional oriented matrix. There's several special cells in this cell complex, in particular the maximal cells. These are called topes. And since points, is there a question? So since points in there lie on none of the hyperplanes, these vectors will actually be just plus minus vectors. There will be no zero. They're a subset of the hypercube, if you want, of dimension E. And so for instance, here, this one cell that I singled out, hopefully is exactly this sign vector, minus, plus, minus, plus, plus, plus. Maybe I did it wrong, I don't know. And now you can observe what happens if you have two cells, two topes, which are adjacent. They are just separated by a single hyperplane. Well, then this means that they just differ in one coordinate, right? Because it's just the points in here and the points on the other side, they just differ in the coordinate corresponding to the hyperplane that separates them. So that's when you start talking about the graph, which is a tope graph. Tope graph just assigns one vertex to each of these maximal cells and makes two of them adjacent if they're just separated by one hyperplane. But since you can also see this as a sign vectors, these are just sign vectors, and the two are adjacent if they differ in one entry. So this is subgraph of the hypercube graph, yes, of dimension E. So note that this actually doesn't really depend on the orientations of the hyperplanes. Yeah, it just depends on the hyperplanes, but not really which side is positive and negative. And actually, I can just forget the entire thing and just remember the tope graph. And this will lead to a pretty rich combination or interaction of combinatorial geometry and metric graph theory, because in fact, what you can see is that the tope graph entirely determines the set of covectors, so the complex of oriented matrix. So that's a kind of, if you understand the tope graph, you understand the whole object. Okay, I will try later to explain how this works. Okay, so this was kind of first introduction, like how does this realizable setting work? I hope this was clear enough. This setting of complexes of oriented matrices is generalizing several previously studied things. And special cases of this in this realizable setting are here like depicted like in a kind of, I don't know, schematic way. So, so what I just said is like you take an affine arrangement and you intersect it with an open convex set, and this will give you a complex of oriented matrix. These actually, in the realizable setting, are also pretty natural. I mean, I will later say that what we really study is not only realizable, but in the realizable setting, these have received some other names in other areas as well. So the combinatorics of such things. The special case, if the hyperplane arrangement is not free, but has to be the coordinate hyperplane arrangement, but then you still have like any convex set, is what was called lopsided sets by Jim Lawrence in the 80s. And the special set where I have any affine arrangement, but I have no convex set, or better, we can say that the convex set is the entire space, yields to what is called the affine-oriented matrix. And finally, if I have a central hyperplane arrangement, any central hyperplane arrangement, but no special convex set, just the entire space, then what I get is realizable oriented matrix. So this, while we have like already seen, like either I can have a special choice in the hyperplane arrangement, but then I have no choice in the convex set, or in these lopsided sets I can do anything in the convex set, but I have very strict choice in the hyperplane arrangement. Now the comms kind of combine both things. It's a free choice in the convex set and in the hyperplane arrangement. So they kind of generalize previous settings. And in fact, there are kind of many things that turn out to be only captured by commas and not by the previous settings. So there's some examples here. So probably you know, or maybe some of you know, that the acyclic orientations of a graph correspond to the topes of the oriented matrix associated to that graph. I don't know, but here the specialization is kind of that now you have a mixed graph where you fix some arcs and then you look at acyclic orientations of the remaining arcs, and these are the objects that you get. For instance, this is an example, and there are some other things like linear extension graphs, for instance, which are tope graphs of realizable comms that turn up here. Yeah. So let's now see what can we say about these sign vectors. So we get slowly getting to a more axiomatic setting. So what can I say about the behavior of these sign vectors that I get from a realizable complex of oriented matrix? They satisfy two axioms. One is called phase symmetry. So let's see what this means. So I have two sign vectors here, and I say that the first composed with the negative of the second should also be a sign vector. So what does that mean? So first, let's just do it like on the sign vector. What does these operations mean? So the negative is just, or the negative, you inverse all the signs. And this composition operation is interesting because it is like you look at the two sign vectors from the left, and if you see a 0, then you take the sign of the second guy, which might also be a 0, but could also be something different. But if you see a sign in the first vector, then you take this sign. Now that's how the operation works. So this is it's an associative operation. And so the claim is that if you have two sign vectors inside, you take the negative of the second one and decompose them, then this new sign vector should also be inside. Why should this work in the realizable setting, at least? So suppose 2 points. You have 2 points which give you two sign vectors here. And now I want to see that the composition X circle minus Y is also inside. So how do I see this? I draw a line from X to Y. And then I go on this line a little bit beyond X. So this now means that, that this I can do because the convex is open. So there's a little space to go. And then all the places, since I don't cross any new hyperplanes, since I'm very close, all the places where X has a sign will just be the sign of X. However, all the places where X doesn't have a sign and Y does, my new point will lie on the opposite side. So it will have like the negative sign there. So this is exactly what happens, why the composition, this phase symmetry axiom holds. That's the first axiom. The second axiom is strong elimination. So this means if I have two sign vectors, it's very similar to elimination, like circuit elimination in matrices, in usual matrices. If I have two sign vectors and they have an entry where they have different sign, then there should be another third covector, which is 0 on that entry. And in all other entries where both of them don't have opposite signs, it should be just a composition of the two. And where they have opposite signs, I cannot say anything. No? I don't ask for anything. And here, similarly, you can see why this should be true in the realizable setting. So just take two sign vectors and suppose there's an element where they have opposite signs. So this means there's a hyperplane which separates these 2 points from each other. So now again, I can draw a line through X and Y, and this will cross the line corresponding to E. And then this crossing point will also correspond to a sign vector and will be 0. It will be 0 on the E's coordinate, and you can also see that it will satisfy these other properties. So it just means it doesn't go too far away from X and Y, basically. Okay, so these are the axioms that are satisfied by the set of covectors of a realizable COM. And now there's a horrible slide a little bit. So on the top, you have these covector axioms again, just what I had down at the bottom of the previous slide. And you just see that the covector axioms for oriented matrices, for affine oriented matrices, and for lopsided sets, they're all special cases of this. Yes, they all have phase symmetry plus strong elimination plus something else. Yeah. So the oriented matrices, for instance, you just have to additionally ask for the fact that the all zero vector is also a covector. And then you have exactly oriented matrices. Affine oriented matrices have a kind of a lengthy additional axiom here, which I didn't want to put because it takes a long time to explain. And you have also lopsided sets, which have an easier further axiom. So it's a common generalization of all these abstract objects. And the question is, how well does actually this axiom system capture the realizable case? So how far can I get away from being realizable? I mean, I can, but the question is kind of how far in a certain sense. So let's see this. For oriented matrices, there's a famous theorem which is called the topological representation theorem, which says that basically every oriented matrix I can represent it by taking what is called a pseudosphere arrangement. So this is, I take a sphere in some dimension, and I take some spheres of one dimension lower that are kind of behaving like straight circles on this sphere, but they are not really straight. They can be a little bit perturbed. And then each of them cuts my big sphere into two parts again. And I can decide, okay, which is positive and which is a negative part. And by this, I can again associate sign vectors to where all the points, and by a very similar idea as in a realizable setting, I will get a set of covectors. And the theorem is that this will be an oriented matrix, and all the oriented matrices rise that way. So this is an important theorem in oriented matrices. So this kind of tells you how far away you get from realizability in oriented matrices. This has a couple of nice properties. For instance, this is, if you look at the phase lattice of this decomposition of the sphere, when this is a sphere, there's a CW complex, it's shellable, it has many nice topological properties as a phase lattice. And when we want from here get to a COM, one thing that we can do is just we can now, for a couple of these spheres, say, okay, I restrict to one hemisphere. I only look at the intersection of some of the open hemispheres and look only at the sign vectors that I get this way. And then you can show, so here I don't know what I did in my drawing, but I just kind of want to say, I think that the blue hemisphere and the gray hemisphere are kind of cut out. And I only restrict to this, I don't know what's called, like a part of an orange, looks like a part of an orange, which is kind of should be an open set. And I look at only at the vectors in there. And then it's easy to show that you still have phase symmetry and strong elimination. So this would be a representation, a nice representation of a complex of oriented matrices. And the question is actually if such a representation theorem exists for complexes of oriented matrices. In one direction is true. I mean, everything that you represent this way will be a complex of oriented matrices, but it's open if every complex of oriented matrices can be represented in this way. There's two. I mean, we conjectured this a couple of years back, but also for lopsided sets, which are kind of a special case of COMs, this was already conjectured by Lawrence in the 80s, and it's open. So let's speak a little bit of operations. So like matrices, also COMs have minor operations, which are pretty much the same thing. So you can delete an element, then this just in the realizable settings just corresponds to deleting the hyperplane from the arrangement. You can contract an element, so this just means you look only on the intersection pattern of this hyperplane. So you lose one rank. And you can define minors. Yes, you just get minors of comms, and these will also be comms. And in particular, all these classes that we have seen so far, they are closed on the minors. In comms, there's one more operation that you can look at, is taking in a half space. I mean, we just did this kind of in the topological setting. So this just means I pick my hyperplane E, and I restrict to one side of it, the open half space. And this will also be a comm. So this is a further operation, which is not allowed in oriented matrices, because then we would kind of destroy the symmetry of them. And you can iterate it, and it will still be complex oriented matrices, and it's then called what's called a fiber. And what you can show that fibers of oriented matrices and affine oriented matrices and complexes of oriented matrices will be complexes of oriented matrices. And for lopsided sets is a special case of comms, which will again lopsided sets. And maybe one last operation that I want to talk about is what you get when you look at a face. So this, you take a point and you just look at the vicinity of this point, and then you look only at the restriction of this, and this will be then an oriented matrix. So that's maybe why I want to speak about complexes of oriented matrices, because the faces will be oriented matrices. Yeah? If I look locally, you see that here you have locally around this point, you have kind of the central symmetry. So you have an oriented matrix. And that's why comms should be called complexes of oriented matrices, I would say. These are not just any complexes. So here's just the top graph from the beginning with the cells filled in. And I have here on the right the phase pose set. That's kind of reversed. I have the topes, the vertices on top, and the edges on the second from top level, and the bigger faces at the very bottom level. And if I look at the face here, then the induced subpose set here has a minimum, which corresponds to having the 0 sign vector, which corresponds to being an oriented matrix. So, and in this setting, there was recently some, not so recently actually, there was some work after ours where some people from combinatorial semigroup theories studied comms as a special case of what they call CW left regular bands. And in our case, this semigroup is just a composition operation. It's an associative operation, and you can define the order through it. And it has the special property, this order, that all the principal filters are CW pose sets, CW complexes. And in our setting, this is the case because they're oriented matrices, and oriented matrices are spheres, as we by the topological representation theorem. So in this setting, they turn out to be like the most prominent cases of these CW left regular bands. There are other examples though. Comms as complexes have more properties. You can kind of decompose them. There's an amalgamation procedure, which I want to just quickly illustrate. So if I pick one hyperplane or one class of edges, in this case, that's all these edges labeled E, then I can, along this set of edges, kind of decompose the comm into two smaller comms that were glued together on a common comm. And this process I can repeat iteratively on the components until I end up only with oriented matrices, with original cells. So not only is every cell a nice thing, which is an oriented matrix, but I can actually glue them together in a nice way to obtain the final object. And this helps to prove a couple of properties of comms, for instance, that they're contractible and such things. Some examples, famous examples of COMs are, for instance, ket-zero cube complexes. Here you see that all the cells are just cubes. This is a special case of a lopsided set. More involved examples of ket-zero Coxeter complexes. Here every cell is a Coxeter sonotope, like I have a permutahedron. And well, these are all examples of COMs. Now I want to speak a little bit about tope graphs. I mean, more. We have seen many tope graphs already in my illustrations. Kind of, I use them all the time. These are just, again, these horrible axioms. I mean, not horrible, but hard to read. What they all have in common, in each of these classes, you take the tope graph. This will be what is called a partial cube. I will tell you what this is in a second. And second, it uniquely determines, or up to isomorphism determines, the set of covectors. So what I said at the very beginning is interesting to study tope graphs because actually it's the same in studying the oriented matrices or the complexes of oriented matrices. It's just one way of encoding them. So let me tell you what this is. So remember, the tope graph is just the incidence graph of the maximal cells, or of the subgraph induced by the topes in the hypercube. But actually, it's a partial cube. This means it's an isometric subgraph of a hypercube. So what this means is it's a subgraph of the hypercube, such for any two vertices of this subgraph, their distance in the subgraph is the same as in the entire graph. This means it has like the same metric than the hypercube in a certain sense, which is a very nice metric because on a hypercube, you know, if you have two vertices and they differ in some entries, then the distance is exactly the number of difference that they have as vectors, as 0, 1 vectors or plus minus vectors. And you have a similar thing here. So how does this work? Well, you have here the partial cube, and now you can color every edge corresponding to its hyperplane. So this gives a partition of the edges. And each part of this partition corresponds to a coordinate of the hyperplane, of the hypercube that we will embed in. Yes. So this, for instance, will be in Q6. And the property that I'm an isometric subgraph means that shortest path never use twice the same color, because in a hypercube that doesn't happen, right? It will never change the same coordinate twice on the shortest path in a hypercube. And since I'm an isometric subgraph, this is here the same thing. Yeah. These colors are called theta classes, often in the metric graph theory community. And so tope graphs are partial cubes, and I want kind of try to explain you the characterization a little bit of what kind of partial cubes they are. So first, in a partial cube, I can look at a convex subgraph of a partial cube. This means it's a subgraph where between any two vertices, all the shortest paths are in the big graph are also in the small graph. Now, this is kind of a generalization of convexity in Euclidean space. And what you can prove in partial cubes that actually every convex subgraph is a restriction of the partial cube. This means it's in the section of half spaces. I will tell you now what this looks like in an example. So here's my partial cube, and now we have here the half spaces. I mean the theta classes, and every theta class cuts my graph into two sides. And I can say, well, I orient these theta classes. Say I point into the positive side with these arcs. And now if I take a convex subgraph, for instance, the vertex is always a convex subgraph, then I can just denote its position relative to each half space with a plus or a minus if it lies on a side, and with a 0 if it's if it contains an edge of this theta class. For instance, here, the edge itself, here at the bottom, is also a convex subgraph, and it lies on some sides of some of the theta classes, but it contains the green theta class, so that will be 0. So here we have already something pretty suspicious, which is kind of, or nice, that if I have a partial cube, then to every convex subgraph, I can associate a sign vector. I kind of want to see when these sign vectors, or what sign vectors I should take, such that gives me this gives me the covectors of an oriented matrix. Another example is the 6 cycle here. It's crossed by 3 colors. Yes, there's 3 series. So convex subgraphs alone are not sufficient for this. You have to get a little bit, have to ask a little bit more of the convex subgraph, and for this you speak about gated subgraphs. So this is another kind of standard term in metric graph theory. So a subgraph is gated, like this G star here, G prime here. If for every vertex outside, there exists a unique gate in the subgraph. This means for every other vertex inside the subgraph, there exists the shortest path from V through the gate to this other vertex. It's kind of a projection. So this is a kind of, I hope you get the idea of this definition. Yes. So in this case, it is a case, and so in my drawing in this partial cube, this is really the gate. The V prime is the gate of V in G prime, and in particular, these graphs will always be convex. And what it means that this is kind of a gate means that on this path, I cannot have any theta class that is also in G prime, because otherwise, if I would go through this path to the gate and then somewhere on the other side of this theta class in G prime, then this wouldn't be the shortest path anymore, because it would use twice the same theta class. So that's a special property that you have in partial cubes, and if you translate it to the sign vectors assigned to this convex sets, it just means that the composition of the sign vector assigned to this convex graph with the sign vector assigned to this vertex is also vertex, is exactly the gate. So this is already a hint kind of here. We have this composition operation which we need to be satisfied by our covectors. And the final class of graphs that we need to look at is antipodal subgraphs. An antipodal subgraph is a graph such that for every vertex in this graph, there is an antipode in this subgraph, such that the subgraph is the interval between these two vertices. This means every vertex in the subgraph lies on the shortest path from V to V prime. And for every vertex in the subgraph, I want such an antipode. So this kind of tells you kind of that the subgraph is kind of round. Yes, everybody has an antipode, such that the whole subgraph is the interval between him and the antipode. So also convex subgraphs. And in sign vectors, you can also express this property. It just means that the antipode of V is just G prime composed with minus V. And if you have now that the subgraph is antipodal and gated, this means I can, from outside, I can take a vertex, I take the gate inside the subgraph, and then I can take the antipode inside the subgraph. And so this means now that I have G prime composed with minus W, which is any vertex, will also be a vertex. So this looks terribly much like phase symmetry, the first axiom that we wanted. And maybe I skip this kind of argument, but the first part of our characterization is that if I have a tope graph of a complex of rounded matrices, then first it determines completely the COM, but I have the property that every antipodal subgraph has to be gated. And so this goes along these lines. And so it actually is a characterization. So I have this big slide again, and on the top I have the theorem for complexes of ordered matrices, and says any graph is a tope graph of a COM if and only if it's a partial cube such that all antipodal subgraphs are gated. And this is a purely graph theoretic characterization of tope graphs of COMs that was not known before. It was kind of a question in the community for oriented matrices. But for oriented matrices, you could also kind of obtain it by a result of Da Silva. And it reads like almost the same thing, just that the entire graph has to be antipodal additionally. So this is, and then the rest is the same. And you can obtain the corollary for affine oriented matrices and for lopsided set as well. And the good thing is that this is not only maybe a nice metric graph theory characterization of the class, but actually you can test it in polynomial time, because these are all kind of metric properties. The thing is that antipodal subgraphs, you don't have too many antipodal subgraphs in a graph because they're all intervals. They're all the interval between one and its antipode. So actually I only have to go, if I'm really naive, I just go through all the pairs of vertices. I look at the interval between them. And then for all the vertices in there, I check if they have an antipode in the subgraph. And if yes, then I found an antipodal subgraph. So at most quadratically many of those. And for this guy, now I have to test if it's gated. But also this is a pretty easy thing to do in polynomial time if I have a distance matrix or something like that, because I just need, like for every vertex outside, there should be this gate such that all the shortest paths go through this gate. Yeah. So it's a polytime algorithm to recognize these graphs, which was also an open problem. So we were happy about that, but there was also a second type of characterization that we got for these graphs. And I want to try to explain you something about this as well. So the thing is that partial cubes and also tope graphs of COMs are closed under an operation which is called PC minors, partial cube minors. And what are these? Well, I already kind of insisted that I have in a partial cube, I have this edge coloring, yes, with the theta classes. And if I take one of these edge classes, there are two things that I can do. I can either contract it, so then I get the graph on the left, or I can delete it, like, but all the edges from the class, and I get two components, but each of them will also be a partial cube. So this operation preserves being a partial cube, and actually it preserves also being a tope graph of COM. So it's kind of an analog of graph minors, but for partial cubes. I mean, it's actually a special case of taking a graph minor because one is contracting and the other is deleting. So you can wonder, like, if I have a class which is closed under minors, what are the exclusions? I mean, what are the minimal obstructions and things like that? So that's what we did. So here we have an example. So this guy is a partial cube, and it's not a COM. Why? Because this blue is a antipodal subgraph. It's actually a 6 cycle. But this red guy, it doesn't have a gate in here. Why? Because every path from the red guy to the blue circle uses one color that also appears in the 6 cycle. The green one is in the 6 cycle, the blue one is in the 6 cycle, the orange one is in the 6 cycle. So all the shortest paths from him to the 6 cycle are not good. So he has no gate. However, if I contract class, or if I restrict to sides of a class, what I will get will be a COM, tope graph of COM. It's easy to check. So this guy is a is a minimal obstruction for being a tope graph of COM. And here are some friends. So these are the obstructions that embed into the Q4. But actually, you can, for every dimension, there is a family, for every dimension D, there's a family of about D plus 1, I think, minor, minimal, partial cube, minor, minimal obstructions for being a COM. And these, you can kind of explain what they look like, describe them. And this then gives exactly the class of obstructions, minimum obstructions for this class. So I give you a diagram. So a second characterization, this describes tope graphs of COMs by excluding some partial cube minors. I mean, this is an infinite family. In particular, there's no Robertson-Seymour kind of theorem for this minor operation in partial cubes. We can also do this for lopsided sets. And there are now a couple of other families which are also closed under partial cube minors. And for a couple of them, we could also determine the set of obstructions, in particular for these on the bottom. Some of them are well-known, median graphs, for instance, distributive lattices. They are very nice classes of partial cubes, and they have very small sets of obstructions. Maybe there's some relation. You can also determine the rank of a partial cube by excluding a cube as a partial cube minor of a certain size. And this corresponds to the rank of the oriented matrix if you go to an oriented matrix as well. But for some classes which are closed on a PC minus, for instance, planar partial cubes, it's not known what the set of obstructions is. It's known that it's infinite, but we don't have a description. It's pretty difficult to find. I'm thinking maybe I can now quickly speak about some things that we kind of attacked using tope graphs. So as I said, kind of the rank of a matrix is just the minimum R such that the graph doesn't have a QR plus 1 as a minor, as a partial cube minor. And the vertex is called simplicial if its degree is exactly the rank of the matrix. So for instance, if I have a rank 3 matrix, then the simplicial vertices will be the triangular topes, with topes with 3 sides in the hyperplanarian.
Can you give a reminder for what QR is?
A QR is just a hypercube of dimension R.
Thanks.
So this is partial cube in particular. It's kind of the clique of partial cubes in a certain sense. And then one of the biggest conjectures, I think, in oriented matrices is that every oriented matrix has a simplicial vertex. So this means every hyperplane arrangement, for instance, of in dimension 3 has a triangular region. But this generalized to all dimensions and generalized to oriented matrix, which is more difficult than just straight arrangements. Yes, it's very open. And for rank 3, we could actually prove it also for antipodal graphs of rank 3. So this is, we showed that like tope graphs of oriented matrices are antipodal partial cubes plus some extra properties. But for rank 3, you could actually also prove it just for all antipodal partial cubes. And here's just an idea how to give you that these are definitely more. Here on the left, you have kind of the numbers of antipodal partial cubes and the oriented matrix tope graphs. Yeah. And we can also, by using a computer, we could show this on this set of partial cubes, which don't all have rank 3. So, the biggest class for which it is known to hold this conjecture of Las Vernas is for a class called Mandel oriented matrix, which I will not really define. But Mandel, he was very active in this area when he wrote his PhD thesis in the 80s. And so he conjectured that maybe all oriented matrices are Mandel-oriented matrices, because this would be very nice. He himself calls this a wishful thinking conjecture, because then by his result, this would prove Las Vegas conjecture, because they all satisfy Las Vegas conjecture. So what we did is, we also using tope graphs, we could show that if a tope graph is Mandel, then not only does it have a simplicial vertex, which he proved, but actually every theta class is incident to a simplicial vertex. So in geometrically, it means every hyperplane is incident to a simplicial cell. Not only does there exist one. And with this, now you can use other results that show, okay, but there are oriented matrices which do not have this property. So they have a simplicial cell, but not incident to each hyperplane. So then this disproved the Mandel's conjecture. And the smallest counterexample known for this is this guy. That's why I like the drawing. So this guy where not every theta class incident to a simplicial cell. Yeah. So this was the simplicial vertexes. Now there's something about corner peeling, but I will skip it. Let me just go to the last slide and speak about some fundamental open things in this area. So the very fundamental conjecture is that every COM arises as a fiber of a norm. Yeah? Or in other words, this is equivalent to the topological representation theorem for COMs. And there's equivalent ways of saying it. I could also say that the tope graphs of COMs all are convex subgraphs of tope graphs of OMs. Yeah? This is another way of phrasing this, or the phase pole set of a COM is a downset of the phase pole set of an OM. These are all equivalent statements. Yeah? But basically, if this would be true, many things from oriented matrices, which are just for free, kind of be given to us for complexes of oriented matrices, and it would be very nice. This is one thing. Second thing is an underlying unoriented theory, and maybe this is interesting for matrix persons. So I mean, for every oriented matrix, you can associate the underlying ordinary or unoriented matrix, and for our affine oriented matrix, something similar can be done. This is called semi-matrix. And for COMs, we don't know. We don't know what the corresponding object should be. And maybe some objects were studied which are called wounded matrices. All of these things on the right have in common that they are in terms of the lattice flats. So they're all geometric meet semi-lattice in a certain way of defining them. I mean, matrices, we know they're just geometric lattices, but for these wounded matrices, you will have a meet semi-lattice where the intervals are geometric lattices. So there's something that I have been wondering, like if there's an underlying unoriented theory and what it should look like. Another thing is about realizability. For instance, we don't know if, so realizable COMs are very nice, but we don't know when we have them. It's in general hard to decide if an oriented matrix is realizable, but maybe some nice classes are realizable. So one of the questions, cat0, if this cat0 property gives you some way of realizing these complexes. Recently, we worked with colleagues about conditional antimatrices. These are also COMs, and they are realizable. So antimatrices in particular, you can represent them by just some hyperplane arrangement dissected with a polytope. And maybe as a last thing, Las Vegas conjecture is kind of ridiculously open, but as we saw, we can even prove it like for lower rank, even for general antipodal partial cubes, which are not tope graphs of oriented matrices, and this should be false. I don't know. In general, it should be false, and one thing that we want to do is disprove even at least this stronger conjecture somehow. And yeah, that's all I wanted to tell you. Thank you.
Thank you very much, Kolja. Do we have any questions for our speaker?
I'm interested in the wounded matroids. It's a very expressive term. What's a wounded matroid?
Yes. So there's actually two things. So I also like I like the term. So there's something called a bouquet of matroids, which is a semi-lattice, such that every interval is a geometric lattice.
Okay.
Yeah. And one way of getting such a thing is just take a geometric, take a downset of a geometric lattice, an ideal, an order ideal. And this is what they call a wounded matroid, because, well, you start with a matroid and you kind of cut out stuff, yes?
Okay.
And it's very similar, actually, to the thing cutting out of an orange matrix and getting a comb. And their big conjecture, I don't know big, but the conjecture in this field is also if actually every bouquet of matrices is a wounded matrix. It's a very analogous problem to the one that I stated here on the top as a fundamental conjecture. It's kind of the unoriented analog of it.
Thank you.
And I mean, if you take, just since I'm talking already, since you take the faces, so the covectors of the COM, and now you only look at the zero sets of them. So the sets for every covector, just a set of elements which are zero, and you order them by inclusion. What you will get will be a bouquet of matrices. And the question is, if you get something more special than that, where maybe you can show that will be a wounded matrix, or I have the impression that these bouquets of matrices are very wild, and there should be some class which behaves nicer.
Winfried, I see you have your hand up on your Zoom. Do you have a question?
Sure, thank you. First of all, thanks, Kolja. I'm looking forward to meeting you at Monday. And the things with the bouquet of matrices is very interesting to me, because I innocently, as a student, to examine the zero sets of the COMs. But anyway, so concerning the conjecture of Las Vernas,
yes,
the counterexamples, they are approximately only at 3/4 of n. So in the realizable case, you have n of these mutations, yeah, and Jürgen's counterexamples give approximately asymptotically 3/4 of n. So okay, what makes you think that there might be none?
No, I'm not saying that I think there are no counterexamples, or no. What I'm saying that I want to disprove it for antipodal partial cubes, which is a superclass of oriented matrices. Yes.
Okay. Okay. Okay.
I'm just intimidated by Las Vernas conjecture, because too many people have tried it, and this is a much larger class. These antipodal partial cubes. Just I was kind of presuming that we could compute the numbers here. Bragging with the numbers. So this is just the antipodal partial cubes. You have many more of them. So so I hope to find a counterexample there. This is not a counterexample to Las Vernas conjecture. Just strengthening of it.
Yeah. Okay, thank you.
Yeah.
Okay, if there are no further questions, I'll say thank you, Kolja, once again, and I will stop the recording.